Now we ask, okay, well, same situation. When we're at angular position theta, what's omega? Now let's assume that we still start up here, but when we get to angular position theta, what is our angular velocity? So what's our strategy for solving this question? Well, if we know the angular position omega, then we can figure out how far we are below this point. Figuring out how far we've come below this point, we can figure out the potential energy change. So, what I'm saying is, well, let's first find the kinetic energy, okay? The kinetic energy will be equal to the loss of potential energy. Find the velocity, and then find omega, just as we have here. So the key is to find the kinetic energy, and to do that, we say, okay, if we're at some position here, the theta now is this angle, and here's your 4 meters, your delta S from your position of rest up here to this point is this vector. And this vector would be projected onto your net force vector, or vice versa. In this case, we projected our delta S vector here onto the net force vector to get our delta S parallel vector. Now we could as easily have projected the net force onto the delta S, and there's a perfectly valid interpretation of that as well. But since the net force remains constant and the delta S vector changes in magnitude and direction, I've chosen to project the delta S on the F net. Okay, well, that projection is your delta S parallel, the displacement parallel to your net force. On the picture, if this is theta, right there's your delta S parallel. It's the vector from your starting position of the point at which the force is applied to this point. It's the vertical projection of that, the projection of that vector onto the y-axis, as it turns out, because the y-axis is parallel to the net force. So that, well, what is our delta S parallel? We can calculate it directly, or we could calculate the position of this point, which is just going to be at angle theta. It's just going to be 4 meters times the cosine of theta plus times the I vector plus 4 meters sine theta times the j vector. Projecting onto the y-axis, we just get the j vector. And the vector from here to here is just going to be the 4 meters times I plus etc. And I'm not writing that out, but you should, and you should be able to. The essential thing that we need to solve this problem is just this projection, and you can verify that that's going to be r equal to the radius plus r sine theta. And you know I really kind of wrote that down wrong. It's going to be r minus r sine theta, and I'll let you think about why. Okay, well then, the kinetic energy is going to be this, 4 meters times 1, but it's going to be 1 minus sine theta. And then, having calculated this, your velocity is going to be square root of 2 kinetic energy over the mass. And that's supposed to be a capital M. I guess maybe it is, but it should be. Okay, and just as we did over here, okay, we get the velocity, and then we get omega by dividing the velocity by the radius. Now let's go back and just be sure we understand why I wanted the negative here. Sine theta is positive from here up to here. Now if you want the delta S parallel, if you go from a point here to a point here, you're going to be subtracting r sine theta, which is this distance, from the radius r. If you're down here, the sine of theta is negative, and of course you're going to want to be adding r to a distance down here. The distance down here is going to be negative r sine theta. Now, think about that. I'm not going to write it out any more in detail than that, but I will point out that error in sign.